So, have you ever wondered how a company like Google or Amazon manages to process just unbelievable amounts of data every single day? Today, we're going to break down exactly how it all works, and we're going to do it by starting from the very first principles of batch processing. Okay, so to get our bearings in this massive sea of data, we first need a map. We're about to explore this entire world that's really built on one single goal, turning all that raw information into valuable, derived data. Right, so first things first, not all data is created equal. At a really high level, it falls into two big categories, and honestly, understanding this distinction is the key to grasping the entire problem that batch processing was invented to solve. So on one side, you have what's called the system of record. This is the absolute, authoritative source of truth. Think of your main user database. And on the other side, you have derived data. This is stuff that's created by processing that original data, like a search index or maybe an analytics report. And here is the most important difference. If you lose your derived data, well, you can always just recreate it from the system of record. And that is exactly where batch processing comes in. It is the engine. It's the thing that transforms that authoritative data into all these useful derived systems that power everything from faster search results to really complex business analytics. All right, so to really understand how we can process data across thousands of computers, let's actually scale it all the way back. Let's just start with one machine. And we're going to use a set of tools and a philosophy that have been around for decades, but are still, astonishingly relevant today. Now, take a look at this. It might just look like a line of code, but believe it or not, this is a complete and incredibly powerful data processing pipeline. With just this one command, you can chew through gigabytes of web server logs in seconds and find, say, the 5 most popular pages on a website. So how does it do it? Well, each program in this chain does one simple, really specialized job. One reads the file, one extracts the URLs, another sorts them, then one counts them up. The real magic is how the output of one program just seamlessly becomes the input for the very next one. It forms this powerful step-by-step workflow. And this whole idea really gets to the heart of what's known as the Unix philosophy. It's all about creating these small, specialized tools that you can flexibly connect, just like screwing together segments of a garden hose, to build really powerful and complex data workflows. Okay, that's great for one computer, but what happens when your data is just way too big for a single machine to handle? We have to figure out how to stretch that garden hose concept across an entire cluster of machines. That Unix pipeline is amazing, but it hits a hard limit, right? It's stuck on one machine. So to scale up to the truly massive datasets we deal with today, we're going to need a fundamentally new architecture. And for a long time, the answer was a framework called MapReduce. And what is it really? Well, at its core, it's pretty much just a distributed version of that Unix pipeline we just saw. It takes that exact same philosophy of simple, chained operations and just scales it across thousands of computers. Here's how it generally works. The process starts with these map tasks that process chunks of the data all at the same time, in parallel. But the really critical step, the secret sauce, is this phase called the shuffle. This is where the framework automatically sorts and brings related data together. And finally, reduced tasks take those sorted groups and produce the final output. The single hardest problem in all of distributed processing is just this. How do you get all the data about one specific thing, like all the events for a single user, onto the same machine for processing, especially when that data is scattered across hundreds of different servers? Let's make this real. Imagine we want to analyze user activity by their age. Well, we've got two totally separate data sets, a constant stream of activity events and our user profile database. The only thing that links them together is that user ID. And this is the really elegant solution. MapReduce uses that user ID as a common key. So the mappers working on both datasets, they tag their data with this key. Then the magic of the shuffle stage kicks in and guarantees that all records for a single user ID, no matter which machine they started on, all arrive at the exact same reducer. It physically brings the related data together for you. Now, MapReduce was absolutely revolutionary, but it had one big inefficiency. See, it was designed for extreme fault tolerance, which is great, but that came at a serious cost to performance. And this, of course, led to the development of newer, much faster systems. The problem has a name: materialization. So in a big multi-step job, MapReduce writes the entire output of step 1 to disk, before step 2 can even start. And then it writes the entire output of step 2 to disk, before step 3 can start. This is really safe and robust, but it creates a massive bottleneck because waiting for disks is slow. So, modern data flow engines like Spark and Flink, they do something much smarter. They look at the entire workflow as one single job. And whenever possible, they just stream the data directly between the steps, right in memory. It's much, much closer to that original, super efficient Unix pipe, but now it's running across a whole cluster. And this makes them significantly faster for a lot of jobs. So, batch processing is incredibly powerful for deep analysis of historical data and answers questions about the past. But this leads to our final question for today. What happens when your data isn't a stagnant lake, but it's a constantly flowing river, and you need to react to events as they happen? For that, you have to leave the world of batch processing and enter the stream.